While we wait to see if there's any stragglers, is on your own. What was it, 8.5? The question says, a chemist decides to produce carbon dioxide gas using the following reaction. If the chemist wants to make 8.2 liters of CO2 gas, how many liters of hydrochloric are required? So in stating that the chemist wants to make 8.2 liters, given the balanced reaction equation, how many liters of hydrochloric acid are required? How would we go about solving this problem? Any ideas?
Would you change it into moles, the 8.2 liters?
Well, we're going to change liters into moles later. That's even more advanced than changing mass into moles. Using density. We'll get into that soon. Right now, we've just been given 8.2 liters. Go ahead.
Would you write the relationship?
Yeah. Remember the Gila-Sock? But we were going to assume what? What don't you know? You need to know if it's a gas or not. So if I told you that this is hydrochloric gas, and this is carbon dioxide gas, you kind of assume that carbon dioxide is a gas. Why? Because at the temperatures and pressures that we live at, carbon dioxide is a gas. But carbon dioxide can be a liquid and a solid as well. Right? So you kind of assume we're talking about where we live, in the domain that we live at. Okay. If I know that these are two gases, I can relate them by volume using Gila-Sock's law by using the straight same technique that we've been using for moles, right? Mm-hmm. What is the relationship between hydrochloric acid and carbon dioxide?
2-to-1.
It's a 2-to-1 relationship, right? And as I'm going from 8.2 to the unknown in this direction, my multiple becomes 2 over 1. I'm going to write it as 2 over 1. I want you to remember that that 2 over 1 represents what? 2, if we're talking about count, this is 2 moles of hydrochloric over 1 mole of CO2, right? Because that's what we're relating. In this case, though, we're not relating moles to moles. We're using Gila-Sock. And Gila-Sock is going to tell us that this is liters to liters. 1 liter of hydrochloric acid, 2 liters of hydrochloric acid for every 1 liter of CO2. So using that multiple from 8.2 times 2 gives us 16.4. So 16.4 liters of hydrochloric acid gas is needed in this balanced reaction to produce 8.2 liters of carbon dioxide gas. Now, if I extend the question and say, how many liters of sodium carbonate are needed?
Would you relate that with water with H2O?
Do the same thing with H2O, sure. But what do I need to know before I can compare liters to liters? Is it a gas? You need to know the phases. If I told you that this was actually a solid, this is a solid, and this is a gas, can I solve for sodium carbonate in liters?
No.
No, it's not a gas. It's a solid. Therefore, I cannot use Gila-Sock to solve for the volume of sodium carbonate. Can I solve for the volume of water vapor, though?
Yes.
Sure, because it's a gas. So I can use Gila-Sock's law and use the relationship to solve for the volume of the water vapor. Now, if I were to tell you that these 8.2 liters happens to be, and I'm just making something up here, it happens to be 5 times 10 to the 5th moles. Now I'm working in moles. Which of the elements can I solve for in moles? If I, rather than given liters, if I were given moles, which of these reactants or products can I solve for in terms of moles? So if I'm trying to make 5.5 times 10 to the 5th moles, can I solve for how many moles of sodium carbonate I would need?
Yeah.
Yes, I can. And I can solve for hydrochloric acid, and I can solve for sodium chloride, and I can solve for water. See, with moles, the piece count, how many there are, I can solve for every single reactant and product. For liters, using Gay-Lussac, I can only consider the gases. I can't say anything about sodium carbonate, sodium chloride, can't say anything about them if all I know is the volume of carbon dioxide. Now, if I knew the density, or if I knew how many moles per liter, I could change liters to moles, get this number, and then solve for everything. See that? But not given that, all I can do if I'm trying to make a statement about the liters, it doesn't make sense. These are solids. They're in a salt shaker, right? Generally think about liters in terms of gases and maybe liquids, but not solids. Solids tend to be in grams. But it's just a reminder about Gay-Lussac. It can only be used for those products or reactants that are in the gas phase. Let me take attendance and we'll move on from there. Seth and Rachel. Okay, for long-term planning for the class, no card here, what's the current plan? Right now, up to what we've covered right now, so this is, we're going to add some things by the end of the day, but as of right now, you should be able to do review questions 1 through 6, practice problems 1 through 7, and extra practice problems 1 through 6. Remember, the extra practice problems, those first 6 are all about relating masses. And we finished with masses yesterday. We're going to spend today and probably tomorrow just working on that same concept of relating mass to mass. Because if you remember, we said up here, we cannot make relationships based on the stoichiometric coefficients between masses. Stoichiometric coefficients relate all of the product and reactants based on moles. It relates all of the gases using Gay-Lussac by volume, but it cannot use mass to mass directly using the balanced reaction equation. If you look on page 292, and I had started using this technique, kind of stumbled upon it myself, using this technique. I'm not saying it's new to me. Other people have done it before. I kind of looked at the way I was solving these problems and came up with a pattern to use all the time. But if you look on page 292, they kind of give you that same kind of graphical idea of what I'm talking about now. You see how you've got the vertical step down, horizontal step across, a vertical step up, going from mole to mole. Do you like the little moles in the book?
Yeah.
Okay, moles, good. Okay. So from moles to moles, and that tied in directly, graphically, with what I've been doing using this technique here. See the vertical lines, the horizontal lines, the arrow moving back and forth, but recognizing that the moles are at the bottom level, and we're going to use other information to get to moles. That's the case here. I'm going to go ahead for right now and just write the chemical formula for example 8.7 on the board. We'll discuss that. But I used the base equation just to go over a couple principles of this graphical method to make sure we keep it straight. So we're going to have glucose, C6H12O6. Okay, what can you tell me about that reaction right there? What is it? It's a combustion, right? We're going to assume it's going to be complete, but from this we know it's combustion. You've got a carbon, hydrogen, oxygen chain fuel reacting with oxygen to produce. Assuming there's enough oxygen, you will get carbon dioxide and water vapor. I know it's repetitive, and it's redundant, and I keep repeating myself, okay? But I want you to make sure you understand this because this is such a common mistake. So whenever I was actively preaching, when I was a pastor, I would say things over and over and over and over. And I was encouraged by my mentor to realize that by the time I'm getting sick of hearing myself say something, that means that most of the people are just starting to hear me. And so frankly, I'm really sick of saying what I'm about to say. But because I'm sick of it, that means some of you are starting to hear me. When I say, looking at this balanced reaction equation, I can say that one molecule of glucose reacts with 6 molecules of oxygen. And in this combustion reaction produces, complete combustion, you're right, because it produces 6 molecules of carbon dioxide and 6 molecules of water. I can also say that 1 mole of glucose reacts with 6 moles of oxygen to produce 6 moles of carbon dioxide and 6 moles of water vapor. Now, if I knew glucose is a solid, if I knew that this was a gas, that oxygen was a gas, the carbon dioxide is a gas, and that the water vapor is a gas, if I give you those things, I can say that 6 liters of oxygen used in this reaction will produce 6 liters of carbon dioxide and 6 liters of water vapor. But I can't say anything about the volume of the glucose because it's not in gaseous form. Well, example 8.7, we're going to start now working again on moving between the balanced reaction equation and using mass with stoichiometry. As I said, yesterday, when we do, let's say in this problem, what are we going to relate? Let's see. We're going to relate simple sugars, excess oxygen, grams of water. Okay, so it's going to be relating grams of water and we have excess oxygen, so the glucose. We're going to make some relationship between these two. Right, so we're going to relate water and glucose. And because in stoichiometry we're looking at moles to moles, stoichiometry is always relating moles to moles. Gilasoc is an extension, liters to liters, but think in terms of moles to moles. So for the vast majority of the time, you're going to put the amount of each of the molecules or elements in question on this lower line. So this is going to represent a certain number of moles. This point over here is going to represent a certain number of moles. And when we're relating moles to moles, we do it by their relationship one to another, right? In here, what is the relationship between glucose and water? 1 to 6. You get that from the stoichiometric coefficients of 1, the implied 1. Remember, if there's no number there, it's an implied 1. So it's 1, 2, 6. Meaning that if I'm given water vapor and I'm trying to compute for glucose, I'm moving in this direction, and moving in that direction, my multiple is going to be 1/6, which represents 1 mole of glucose, glucose, C6H12O6, per 6 moles of H2O. And if I'm moving in the other direction, my multiple becomes 6/1, which is 6 moles of H2O for every 1 mole of glucose. Okay? Those are my multiples. So if I'm going from water to glucose, it's times 1/6. If I'm going from water to glucose is 1/6. From glucose to water, it's going to be 6. That's going to be my multiple. Now, I can only relate moles to moles. In the question here, let's go through and read it. It says the human body produces the energy it requires to live by burning simple sugars such as glucose, according to the following chemical reaction. And there you have it on the board. This reaction produces a lot of heat, which is used to power all of the body's motion. When the sugar is burned, the carbon dioxide produced is exhaled. So when you breathe out, that's the CO2 on the product side, while the water produced is mostly eliminated through your urine. Now, if the average human burns about 1.2 kilograms, we come over here and say it's 1.2 kilograms. I'm writing 1.2 kilograms for the simple sugar above the horizontal line. Why am I doing that? Because if I were to write 1.2 kilograms down here as a technique, some of you would start relating mass to mass using that multiple, and that's not correct. This line here is reserved for our purposes for moles. So I've been given 1.2 kilograms, I need to get it into moles. Continuing on. Simple sugars each day, 1.2 kilograms of simple sugars each day in excess oxygen. By technique, I'm going to go over here and say excess oxygen. Now, what do I learn from that statement, excess oxygen?
You won't, yeah, we won't run out.
We won't run out of oxygen, right? So the limiting reactant is going to be the glucose. There's plenty of oxygen, so don't worry about it. That also tells us, if they just said combustion, since there's plenty of oxygen, we know it's going to be a complete combustion. Because if there were insufficient oxygen, rather than carbon dioxide, we would get what? Carbon monoxide, right, if there were insufficient oxygen. So think about that. How would you get insufficient oxygen in your body? Either there's not enough air in the room, or you've got something obstructing your airway, right? So part of the choking process is changing what you produce from carbon dioxide to carbon monoxide, which is poison. Okay, so you can think through the implications of that on your own. So 1.2 kilograms of simple sugars are combusted with excess oxygen. How many grams of water does the average human eliminate then? Grams of water. How many grams? So I'm given kilograms of glucose, the simple sugars, and I'm asked for grams of water. Notice that I also put the grams up above the horizontal line. I don't want to confuse myself. Now, I could have given you the question, given a certain amount of kilograms, how many moles of water? In which case, as you work this process, you'll stop at a different place. But we're given kilograms, and we're asked for how many grams? So, remember we talked about yesterday, what is the key of translating a mass into the moles? There's something we're going to look for every time.
Is it AMU?
It's related to the AMUs, yes. That's the unit. It's known as the molar mass. So we're going to use the molar mass as the Rosetta Stone. It's the key that's going to help us translate from kilograms into moles. And remember that the molar mass for every element and molecule is unique. You got to compute it every time. Which is why the last previous module we went through and said, okay, what is the molecular mass of glucose? We need to go through and figure that out, right? We come over here to the periodic table and say, well, that molecule of glucose is built up from 6 carbons. So come over to carbon, you're 6, it's 12. So the 12 AMUs per atom of carbon. I have 6 of them, therefore there are 72 AMUs of carbon in this molecule. Then hydrogen. Well, there's 12 of them. Each hydrogen is 1.01, so there's 12.12 AMUs of hydrogen in every molecule. And then 6 oxygens, and each oxygen is 16 AMUs per atom. We need 6 at 16 each. And so we add all of those up. What's the book say? 180.1 AMU per molecule, right? 180.1 AMUs per molecule. Does that directly help you between kilograms and moles? Mm-mm. But if I know how many AMUs per molecule, what do I also simultaneously know? AMUs per molecule, it's the same number, but what are my units?
Grams and moles.
Grams, right, so it's the same number of grams per mole. So if a molecule of glucose, if one molecule has a molar mass of 180.1 grams per mole, or excuse me, 180.1 AMUs per molecule, it also has simultaneously 180.1 grams per mole. See? So I'm given grams per mole, and I'm looking for moles. We can also forecast on the other side. We're going to need what? We're going to need some way to translate, because we know we can compute the moles, and the moles are going to give us the moles, and we need to go from moles up to grams of water. So we're going to need to know the molar mass of water. Oxygen is 16 AMUs per atom. Hydrogen is 1.01. So for our purpose here, we can just say that this is 18.02, so it's basically 18. 18, we're going to use the units grams per mole. See? So on this horizontal section here, I want you to write down what is your conversion? What's your Rosetta Stone? How are you going to translate between these two things? To go from mass to moles, we've got to do something with the molar mass of the molecule in question. And on the other side, when we go from moles to mass, we need to do something with the molar mass of the molecule in question. Here we're given 1.2 kilograms of glucose. We need to know how many moles of glucose we have, because until we have the moles, we can't use stoichiometry. We've got to translate it to moles first. You notice in the book on 293, they go through this, that we have 1.2 times 10 to the third grams. See, that's the way to write kilograms, right? 1.2 kilograms is the same as 1.2 times 10 to the third gram. For every kilogram is 1,000 grams. Page 293. How do we go from mass to moles? You can see on there that we're going to divide by the molar mass. So as we go from top down, our process is to divide. Top down, we're going to divide. We've got 1.2 times 10 to the third divided by 180.1 grams per mole. That's going to give me units of mole. I'm going to have grams divided by moles. You flip the denominator, you end up with moles. That's going to be our unit. So we say, yeah, that's right. It's going to end up being right. The book says that the result of this is 6.7. So a couple modules ago, I may have said, you have 1.2 kilograms of glucose. How many moles of glucose do you have? And you would have done this process to bring me to this point. This is review. There's nothing new here. Okay? So I can take grams, divide by the molar mass to get the number of moles that are in that same sample of that molecule. Now that I'm on the moles, the horizontal line, stoichiometry is this conversion factor. So I have 6.7 moles, and I'm moving from left to right. I'm actually going in that direction, so my multiple is 6 moles of water for every 1 mole of glucose. Multiple of 6. So I've got 6.7 with a multiple of 6, and that's going to come out to be 40. Actually, 4.0 times 10 to the first is what they have in the book, but that's 40. 6 times 6.7. 6 times 6 is 36. 6 times 7 is 42. It's between the two. It's 40. That's 6.7. A little bit more than halfway between times 6 and times 7. So 40 moles, or 4.0 times 10 to the first moles of water produced. This we've done in previous modules. This we've already done in this module, converting from moles to moles. I was given, and I've been asked for. I'm not there yet, am I? I can tell you right now that when I have 1.2 kilograms of glucose in this reaction, it will produce 4.0 times 10 to the first moles of water. But I was asked for how many grams of water that is. And so we now need to move from the moles line, and we move vertically up to what we've been asked for. Notice that over here, going from top down is a process of division. What do you think it is to go in the opposite direction? Multiplication. So multiplication, do you like multiplication better or division better? I tend to think multiplication. I know they're just the inverse of each other, but multiplication, so I like multiplication. Oh, multiplication is up. Right? It's corny, but if it works, use it, okay? Multiplication is up. Multiplication is up, therefore division must be moving down. So, given that we have 40 moles of water produced, I was asked for how many grams of water is produced, and so I'm simply going to take the number of moles of water produced and multiply it by its molar mass of 18 grams per mole. Moles times grams per mole leaves me with grams. 40 times 18 is 720, or 7.20 times 10 to the second moles. Or excuse me, grams. 40 times 18. 4.0 times 10 to the first, 40, times the molar mass of 18 grams per mole will give me 720 grams of water. Notice that 1,200 and 720 is not in a stoichiometric relationship. You don't get that from the coefficients. You can't get it from the coefficients, which is why you have to go from grams to moles, moles to moles, moles to grams. Okay. Any questions on our process there? No? One more time. I'm sick of it, which means you're starting to get it. Here we go. Grams go on, you have a balanced reaction equation. You read the problem, you write a vertical line underneath the stoichiometric coefficients of the molecules in question. You then write down what is given. If it's moles, you write it on the horizontal corner. If it's grams, you write it beside the molecule. You write down all the information that you're given. You write down what you're asked for. If it's moles, you write it down on the horizontal line. If it's mass, you write it just below the molecule. You put in, between those molecules, you put in your stoichiometric relationship. You compute the molar mass of the molecules in question and place them on the next to the vertical line on both cases. Then note that if you're moving in this direction from top to bottom, you're going to divide by the molar mass. And if you're moving horizontally up, you're going to multiply by the molar mass to convert between grams and moles to grams. That's the process. That's what you're going to do on every single problem. So now it's just a matter of practicing the process. Yes, sir?
So how do you know when you're moving down?
Because if you're given mass, you've got to move down to get it to moles. So it's going to be mass, moles, moles, mass.
You're given moles.
If I'm given the number of moles and a match for the number of the mass, I start from here. Now I can move left and right, and the path to let me move left and right is the relationship stoichiometrically. That's what allows me to move across this line. What allows me to move up and down is knowing the molar mass. So the first stoichiometric problems we had were all on this line. You were given moles, and you were asked to compute moles. All you needed was the relationship between the two molecules. Now you're given a mass. That's great. I need to find the access paths to get me down to the moles. Because once I'm at moles, I know these numbers and I can move along the line. And then at the other end, I need to get the paths to go back to grams, which is the molar mass of the molecule in question over there. Let's go ahead and run through the same way. Let's run through the second part on page 294, the second reaction, and then we'll finish by letting you work the on your own in class for the rest of the period, okay? Let me erase this. Say again? You may. Notice it's a little cooler in here today? Yeah. Mr. Glenn went through and did some adjusting to our vents. And so we have, unlike other rooms, we've got three vents, actually 4 vents in here actually. He shut a couple of them completely off and he cranked the other ones down. What that'll do is give less heat in here, which is less excuse for the nodding off, okay? And hopefully that heat that doesn't come in here gets pushed to other places that need it more. So I'm going to start, because of that, and just so you know that I have been sympathetic to that and the heat in here, I'm going to ask you to occasionally, I may ask you to stand up. I know it's first period, but the heat issue is going away. And rather than throw markers or pass out the goggles and all that other kind of corny stuff, I'm just going to ask you to stand up. And I would ask you, if you feel yourself nodding off, absolutely perfectly free, don't request it. If you need to stand up because you're nodding off, just stand up and move to the back of the class. Just, put yourself in the back, but stand up. I'd rather you stand up because you acknowledge you're having trouble staying awake than to start drooling and not hitting your forehead on your book. Okay? All right. The second question on page 294 says, we've got 2 HCl liquid and barium hydroxide solids react to produce barium chloride aqueous and water, liquid. All right. And it says the toxic acid spills, which occur regularly in industrial settings, are usually cleaned up with a substance known as barium hydroxide. Barium hydroxide. For example, if hydrochloric acid, here, is spilled, barium hydroxide neutralizes it with the following reaction. And we're going to learn later, this is a classic acid-base neutralization reaction. We have an acid and a base. Hydroxide is your key that it's a base. So it's an acid-base reaction. Don't worry about the particulars of acid-base right now. This is just a reaction, okay? The products of the reaction are not nearly as toxic as the reactants. So as long as there's enough barium hydroxide is used to react all of the spill of hydrochloric acid. If 540 grams of hydrochloric acid, okay, we know we're going to be dealing with hydrochloric acid. If 540 grams of hydrochloric acid are spilled, what's the minimum number of grams of barium hydroxide necessary to completely neutralize the spill? Now, they said in there, and practically speaking, if you were in this industry, you're a safety engineer at this industrial site, you would make sure that you had way more barium hydroxide than you needed for what would typically spill, because you want to have barium hydroxide be in excess. Why do I want barium hydroxide in excess? So I make sure that every single molecule of hydrochloric acid has an opportunity to be neutralized. I want to get rid of this stuff, so I need excess of this stuff. But the question says, at a minimum. In other words, compute the balanced reaction. How much exactly would it take? And then make sure you've got more than that. That's what we're going for. So you see that we're going to use stoichiometry, but it's also going to be, we're starting with grams and we're finishing with grams. So by process, I wrote the vertical lines underneath the stoichiometric coefficients of the molecules in question. I wrote down what was given. It was given in grams, so I put it high on the bar. Over here is asked for grams, so I put it high on the bar. And now we need to solve. So I'm going to connect these two things. And by process, I'm just going to go ahead now on here and put in my relationship, which is what? 2 to 1 by the stoichiometric coefficients. 2 to 1. Right? Now, I know I need to go from here to here. I'm going to go down, across, and up.
How do you do that?
Pardon? Why do I put the arrows there?
Yeah.
Because I'm given this, and I'm asked for this. And my path, I have to follow the path to get there. Right? So I'm going down vertically from mass to moles. So I can always just go ahead right now and put moles here and moles here because I'm going from mass to moles, from moles to moles, and from moles back to mass. So as I move down, my operation is going to be division, and as I move up, it's multiplication. That's right. How do I move from top to bottom and from bottom to top? My Rosetta Stone, my key is what? Molar masses. So I need to figure out the molar mass. What is the molar mass of hydrochloric acid? Well, hydrogen is 1.01, so 2.02 plus a chlorine, and a chlorine is 35.5. Okay, so 35.5 plus 1.01 plus 1.01. In the text, they go ahead and give you that as being 36.5. I'm going to write 36.5 right here to say, first of all, it's 36.5 AMUs per molecule. But for our purposes, we care more that it's 36.5 grams per mole. So to go from grams to moles, the key is the molar mass of 36.5 grams per mole, and I divide what I've been given by the molar mass to compute how many moles, and that turns out to be 14.8. So 540 grams of hydrochloric acid is the same as 14.8 moles. How did I get that? I took my mass and divided by the molar mass to get the moles. My next step along the pathway is mass to moles, moles to moles. Okay, I need to figure out how many moles of that I need for the perfectly balanced reaction equation. 14.8, and what is my multiple? Because as I move from left to right, the first number I'm going to hit is the 2. I'm going to drive that 2 under. We always take the number we hit first and drive it under. So I know that my reaction multiple is going to be 1/2. I'm driving the 2 under the 1. Let's just go ahead right here and put the units in there. I didn't focus on the units before, but this is the link between the way they do it in the book and the way I just do it up here. That 1 to 2 represents what? It's 1 mole of barium hydroxide per 2 moles of hydrochloric acid. That's my multiple. But the actual number is 1/2. It's 1/2 what? It's 1 barium hydroxide per 2 hydrochlorics. So 14.8 times a half. What's a half of 14.8? 7.4. So we're 7.4 moles of barium hydroxide. Following the path. Mass divided by the molar mass gives me the moles. The moles times my stoichiometric multiple, my conversion factor, gives me moles. Now I need to go back to mass, because I wasn't asked for moles. I was asked for mass. This could be a 2-part question. How many moles of barium hydroxide are required? Okay. How many grams of barium hydroxide are required? Computing this, I need some way to get from moles to mass. We've already said that's going to be the domain of the molar mass. Question now is, what is the molar mass of barium hydroxide? So it's the mass of 1 barium, 2 oxygens, and 2 hydrogens. Again, skipping back to the book here, I'll go with their computation of 171.3. 171.3. My units are going to be AMUs per molecule. Simultaneously, they're going to be grams per mole. So now that I have moles and I have the molar mass, I can do the math. I can take the moles and multiply by the molar mass to give me how many grams. And the book answer there is 1.27 times 10 to the third.
So multiply what's the numbers?
7.4 times 171.3 equals 1.27 times 10 to the second. Or excuse me, 1.27 times 10 to the third. That's process, okay? That works for every reaction we're going to do. Everyone, just to know the process. I encourage you to know the process and practice the process, and go ahead and start doing that with on your own 8.6, and just walk through it. Given the reaction equation, write down the given, write down the unknown, compute the molar mass, go from the mass, using the molar mass to moles, use stoichiometric coefficients, and the resulting, conversion factor to go from moles to moles across the horizontal line. Then, under the molecule in question, multiply the moles by the molar mass to give you the mass of the product or the other molecule in question. Same process over and over again. I'll start working 8.6 on the board in just a few minutes. Yes, sir? Mm-hmm. Process clear now? Good with process? Okay, so all the different steps you need to solve it. It's one of those things that if I were the student, I would just, okay, here's my process. Have that process flow in front of you and do it. And just keep practicing until you don't need the process flow. What am I going to do first? Write down the reaction equation. You might want to check it to make sure it's balanced, but in most cases, they're going to give you the balanced reaction equation. Write down the knowns, the unknowns, the horizontal lines, connect with the vertical line, put in your stoichiometric relationship, put down the molar masses, walk from point to point to point.